all on the same page in terms of the peer reviews, where they're not due until next week on Friday. So you have a ton of time. They should really only take you about an hour, like maybe two if you're being extremely thorough. So, I mean, I would certainly like you can just go ahead and get them done, but don't think you're going to have to spend a whole lot of time on these. Um, the way you access them is if I'm going to leave the draft where you turned in your slides. And if you turned in your slides, one, it's going to take me at least a week to get these graded. So um, let me urge patience on that. But you would see your grade here as usual, and you check your feedback the same way as you checked your topic. But once you turn them in, you should see this guy with the glowing red button. Let me say again, you will not be able to access this until your slides are in. So if you have not turned, oh, you can't see anything. Can't see anything because apparently I didn't share my screen. Okay, now you can see it, right? Sweet. And this is just the same place you turned in your slides, which I'm leaving in week 11. So that's how you found those. People out there who have not turned in their slides, you are not going to be able to access these reviews until your slides are in. So please turn your slides in. But you just click there, and you should have two projects to review. To review a project, you just hit the review button, or the start peer review. That'll also work. It pops up in the new window, so make sure that don't have pop-ups blocked. And you'll see, I think 4 questions. I have 4 questions on here. 4 questions that you need to answer, where you'll notice that there is a word minimum that you are supposed to hit. I don't think this will tell you whether you've hit the correct word count or not. So if you go over to some other text editor, you can just type out your text in there and make sure you hit the right word count, and then just copy and paste it into here. You can save your work if you get interrupted in the middle of it. Once you are completely done, you need to hit the submit button. Please do not hit this button until you are completely done, because I cannot undo that button. So if you hit that button at that point, we're going to there will be a complicated email chain that I have to set up. So please don't hit that button until you are truly done with your reviews. Okay. Yes, this is for the peer review. Okay, but yeah, so you'll have 2 of them. I think overall it's like 200 to 250 words. And let's talk about what you have to do 2. They're due next week on Friday. So they're due week 13 on Friday. And so let's talk about a few things. I'm sure most of you have heard this from me before, but we're going to go through it again. So the point of these reviews is for whoever slides they are to improve their slides, to have a better presentation, not for you to say whether their slides are good or not. So you're not trying to assign any sort of value. You're not saying this is a perfect project or this project really needs improvement. All you're trying to say is here's what's good about your slides, here's how you can improve your slides, here's how you can make your project better. Sound okay? Okay. So a good way to do that is to stay away from value statements. So not saying this is good or this is bad, but instead describe what about it that you think is good. This is a really nice graph because it really helps me understand the relationship between Lorentz force and radiuses of circles. And the more detail you can give on that, the better. Or I found this slide really confusing because I don't understand from it the relationship between Lorentz force and cyclotron radius. And perhaps maybe you could include a graph or a free body diagram. Let me say it's really nice if you spend as much time on the good parts as the bad. So if you come across a presentation that you think is just perfect, that they did an excellent job, that everything makes perfect sense, a good thing at that point is to go through and say why you think it's so good. Because a lot of people, while they put together a good presentation, don't realize why it's so good. And so, hey, I'm really looking forward to hearing the explanation of this graph. This graph is super interesting because X, Y, and Z. Okay. Okie dokie. So homework and quiz. Yeah, homework and quiz due this week. So I got comments coming up that I don't have here. I do have a rubric on how I am going to grade your reviews. And so you get a point for submitting something. You get 3 points for hitting the word count. So do make sure you're hitting word count. More points for being thorough and complete. And so this is when I read through your review, does it just say, hey, this is really good, like 20 different times? Or does it go into detail? Can I tell from the review which project you reviewed? And then like respectful and constructive remarks, where I do want to talk about this for a little bit. I did assign 3 points just for being respectful and helpful. But let me say, if I do come across some reviews that I find are just rude and mean, that person is getting a 0 on this assignment. So so there are 3 points assigned to being helpful and respectful, but also if I find a review that is just not nice, that person is going to hear from me. Sound okay? Okay. Given all of that, let us talk about what we want from the reviews. So can all of you take a minute, think back in your history to a time where you did peer reviews or got some feedback or went through some similar process that was really helpful, that made your work better, that you came out of it really happy that you went through that process. And think about what made it so good. What particularly about that process made it stand out in your mind as a good experience. Okay? I'm going to give you a minute to think about this. So at 2:15, we're gonna share our thoughts. Online people, go ahead and just type it into the chat, and you guys can hit enter in a minute. But I want to go through and I want to hear from everyone what made their past peer reviews good and what they would like to see from this peer review. Take a moment to think. Have you guys thought? Okay. What made your past, what good things are standing out to you?
Past more advice. Like if there is something wrong, try to like explain why it's wrong or he said what you could do to try to fix it. Or
Okay, I like that.
confusing, just ask like what you're trying to do. Like, try to explain it to them.
Okay, so don't just, a lot of people, while they're trying to be nice, will skip over any bad points, but that's not helpful. If there is something wrong with the slides, definitely like bring it up and try to thoughtfully explain what went wrong and possible ways to fix it. Excellent. What else? Max, let's hear something.
What was helpful?
Yes.
Okay, so it was a history project, and we were working on like a pioneering Indian chessboard game.
Nice.
But then again, we had to write a report.
Uh-huh.
And the most helpful advice I got from them was someone helping me fix my grammar on it.
Oh, actually, that's really valid. Yeah, definitely just like spell checking somebody's work is super helpful. I like it. What else?
Positive feedback.
Positive feedback. Always nice to have something positive to say. I concur. Online people, any any positive things that you want to throw into the chat? Because there's a few things that I haven't heard yet, that I'm kind of hoping to hear. Yeah. I like that. Okay. Excellent. That was definitely one of the things where like detail, just vaguely saying something's confusing or something's really good isn't as helpful as saying what it is that confused you, right? Um, so avoid vague statements, add as much detail as possible. And also that really helps hit word count. I've had a lot of people tell me that it's hard to hit word count on these things. If you're having a hard time, go through your reviews and every place you see that, this was good or this was confusing, add another sentence about why. Sound okay? Okay, so what I got is, say something nice, say something specific, and give suggestions on how to fix things. Excellent. We're going to do the same thing again, but I want to hear the things that you don't want to happen. So the worst peer reviews, the worst feedback, the sort of things that you are really not looking forward to seeing in your reviews. So take a moment, think about it. At 2:19, we will continue talking. Okay, bad things. What don't you want to see?
Not offering a solution.
Not offering a solution. Okay, I like it. What else? Yes. Ah, not helpful at all, was that? Okay, so I do definitely want to talk about this one. Even if you come across a project, and I'm sure yours was like wonderful, right? It was a great project. I bet you made an A. But just saying this is really good isn't super helpful. Like even if you want to say, okay, you hit all the requirements, you can say, hey, I think you hit this requirement because you did this thing, and I think you hit this requirement because you did this thing. Um, and if you think something is good, really do tell the person why you think it's good. Like what's really great about that project that you think so highly of it. Because honestly, a lot of people don't know why their work is so good, and so it really helps to say, okay, here, like let me describe exactly why it's so great. Okay, what other negative things?
Yeah, I have before, like some people like just use like not do it.
Say again?
Like it's like nothing like really helpful, just like saying like not do it or like
Ah,
just straight like nothing really active for group.
right, yeah, definitely. Like it's always going to come back to detail where people are totally willing to hear negative feedback or positive feedback as long as it's useful. And so definitely, I like to say, if your roommate or your friend said, hey, could you proofread my paper? You wouldn't just say, hey, this is good or this is bad. You would try to make their paper better. And so definitely approach these as how are you going to help this person make their presentation better? Online people, would you like to add anything? A lot of online people, but they're quiet. Okay. Um, okay, I like this all. Okay, so uh, stay away from vague statements, stay away from unhelpful statements, be detailed. Um, only thing. Oh, actually, that's a really good point. I have occasionally like read someone's, okay, so saying that they're recommending to do something over the top, where occasionally I read people's review and they're like, but have you thought about building in a huge thing or taking these intricate measurements? And definitely when you're making your suggestions, suggesting that someone spend hours and hours and hours doing a small portion of the project might not be super helpful. So try to keep it within the realm of reason. And if you're at a loss to think of what to recommend, a lot of times, if you just describe precisely what you're seeing, that sometimes leads other people to make the correct recommendation to themselves. So describing precisely what you see, like I see that you did this step, and I see that you did this step, and I see that you did this step. I don't see any data, but I'm not sure how you want that to fit into your project is fine, because then they can make their own conclusions. Saying that their project is the worst and they have to redo it. I'm so glad someone brought this up, because this is exactly the sort of thing that I occasionally see and I do not want to see. Okay, that's not helpful at all. Even if you do think that they should redo the entire presentation, don't say that. Instead, say, I think your introduction slide could use this. I think your analogy slide could use this. So redoing the whole slide is vague and unhelpful. Specifically saying what you would redo if it were your slides could be helpful. And don't use the word worst. Sound okay? Okay, yeah, excellent. Okay, anything else? Okay, I feel pretty good about this. I think you guys have a decent idea of what I want to see. Um, are there any questions on how to do the peer reviews, or how you're going to get a good grade on the peer reviews? You can all access them and you feel confident in your ability to complete this assignment.
Once we are done with peer review, is there like to see that peer review? Where are we going to see the peer review?
Oh, okay. After someone submits your peer reviews, you're going to go back to the same assignment. And I forget exactly where the button will be, but I think it's going to be the same, like the peer mark review button, where you'll see two reviews for yourself. And let me say, there's always a few students who don't get reviewed just because someone doesn't turn in their slides or something like that. If you're one of those students, please let me know so I can give you some feedback myself. Okay, good. Any other questions, concerns, anything else? Feeling good? Okay. Okay. those are the peer reviews. They're not due until next week on Friday. If you have any questions on them, we of course will have time next week to go over them. Should only take you an hour or two, so please just like knock those out at some point. This week, today, I'm hoping to finish up chapter 13. Thank you, chapter 13. We'll see. I think we can get through it. It's not too long of a chapter, but I do want to make sure everyone has this idea of induction down really well. So the chapter 13 homework, definitely do this Friday. Expert TA, your quiz this weekend will be over chapter 13. Okay, then let's go ahead and share the screen. Okay. So where I think we left off is we had the definition of Faraday's law really thoroughly worked out, where an EMF was generated by a change in magnetic flux through some area. We had the idea of Lenz's law, where a current would be created from this EMF that would try to oppose the change in magnetic flux, either by opposing a magnetic field or supporting it. And I think we had done a few problems. Does that sound kind of where we are? Okay, excellent. So the next thing I wanted to look at is I want to look at electric fields. Now, for two reasons. One, there's a problem that we need to get through in the homework that's a little bit confusing. But two, by the last week of this class, what we really want to talk about are just electric and magnetic fields. We want to get away from charges. We want to get away from wires. Just move away from all of that and just like down to the bare bones of I have an electric field and I have a magnetic field and how do those things interact. And so starting from Faraday's law, let's talk about how this kind of boils down to an electric field and a magnetic field. Where on one side of this, my flux is really dependent on that magnetic field. So we see one side of this equation, d phi b dt, really being the derivative of a magnetic field dot area with respect to time. And then on the other side of this equation, we have an EMF, a voltage, where you might or might not remember that an electric field is really the change of voltage over a change in space. So how a voltage changes with respect to space, where electric fields always point from areas of high potential to areas of low potential. Is that familiar? Okay. And you could write this, of course, as how much the voltage changes over a region is the electric field times the length the electric field is spread out over. Okay. Which let me throw that on my next line here. So there's my electric field times how far the electric field extends over. So this EMF becomes E delta X. And so kind of just to note here, there's a few things about this equation that we will talk about in much more mathematical detail at the end of the semester. But here's an equation that relates an electric field directly to a magnetic field. It's not It's not that there are charges moving that are generated by this electric field that cause a magnetic field. It's that I have an electric field on one side and a magnetic field on the other. The next thing I want you to look at is on one side of this equation, we're looking at how this magnetic field varies with respect to time. So we're looking at this quantity with time as our variable. And on the other side, we're looking at how this electric field works over space. So we have space on the other time of our equation. So on one side, our variable is length. On the other side, our variable is time. And we're going to see that pop up again, where you need to think, when you think about how electric fields and magnetic fields relate, it's both with a spatial component and a time component. Sound okay? Okay, kind of like hold that in your head for like 4 weeks and we'll come back to it. But that's like a really big concept that we will be looking at. Meanwhile, there is a homework problem that would be really good to look at because it asks for an electric field, and this is kind of the first time we've had to do this. So the homework problem I wanted to look at was number 15, where we have a toroid. So I have this sort of thing right here, and I have a wire looped around it. So you put a current through this wire, you'll make a magnetic field. But we've kind of cut a chunk out of a toroid, and that's the area we're going to care about right now. So my current's going in like that and out like that. Whoosh. So it's going around like that. Let's look at this area right there. My magnetic field's either going to point towards the top of the page or the bottom of the page right there. Which way is it going to be? Yeah. So top of the page. So you take your hand and you curl your right hand and you curl your fingers around the direction the current's going. And then you point your thumb. My thumb is pointing towards the top of the page because my fingers have to curl around with that wire. Okay, so we're going to have a magnetic field this way. And that magnetic field is going to extend throughout this whole ferromagnetic core. And in fact, it's even going to extend in that region of space there. Because I'm sure you guys have completely gotten that magnetic fields make loops, right? That was a big thing in lab last week. Magnetic fields make loops. And so these, if you have a magnetic field in the rest of the circle, it's certainly going to bridge that gap. Excellent. Okay. But this wire that's carrying a current, this current is going to vary with respect to time. And we're really not going to tell you how it varies with respect to time, but we will tell you it'll vary with respect to time so that the magnetic field will change with respect to time. So this magnetic field is going to change with respect to time at the rate of 0.011 Teslas per second. Sound okay? And you're really not going to need to know what's going on with the current at all. You're just going to need to know this number, which for this problem we're going to call R sub 8. Sound good? Okay. Next thing, we're going to look at a point right outside that magnetic field, where we're going to say that the radius I should have drawn this slightly bigger. The radius of those iron cores is going to be R1. And the radius from the center of this out to this point is going to be R2. Okay, so R2 is slightly larger, just like a little tiny bit larger than R1. Does that make sense? Okay. What we want to find is the electric field at R2. Sound okay? Okay. And this might be a little bit confusing, and so let's do like a suppose here. So I have these two iron cores here. They're making a magnetic field, so I have a magnetic field through here like this. I care about this point right here. And so first let's define the area that we care about. One really easy area to talk about would just be a circle with radius R2. R2. Make sense? Because we could find the flux, the magnetic flux through that circle. We could just say, well, the magnetic flux through R2 would be B dot A. And what would A be in this case? Pi R squared. In particular, pi R2 squared. Okay, such that if I wanted to know something about the EMF here, the voltage that it generates, I could easily just take the derivative of that. Does that make sense? And really quick, let's look at that. If I'm taking the time derivative of B pi R2 squared, pi is definitely a constant. It's going to come out front. What about R2? Is that a constant or a variable? I like constant because it's a length, and I'm going to keep looking at that same point. So the only thing that's really changing with respect to time is this B. So I have pi R2 squared, the time derivative of B. And remember, that's the one thing that we just know. So we could just plug in that number if we needed to know it. Okay. But we didn't need an EMF. We needed an electric field. And so let's visualize this electric field. If, for example, this green loop was actually a wire, right? So let's say it could be a current carrying wire. It looks like my magnetic field is increasing, right? Because the rate of change is positive. So my magnetic field right here is increasing. Which way would this loop of wire want to make a magnetic field? So my loop of wire sees an increasing magnetic field to the right, and it wants to stop that. So which way does it need to make a magnetic field? To the left, because that way it would stop the change. Does that make sense? Okay, so it wants to make a magnetic field. Shouldn't you use blue? That way. Okay. Which means it needs to, let me do this on my, it needs to make a current like that. And can y'all see my drawings? So yeah, if you put your finger in the direction of the current, curl your fingers around, It would be going down on this side and up closer to you. Sound good? Okay, okay. All right, which means that this EMF would really look like a battery with the positive edge on that side. Which means that if it were making an electric field, it would make an electric field pointing away from the positive and towards the negative. Does that make sense? Okay. Okay, so we can kind of visualize what this electric field would look like now. And now the thing is, even if there's not a wire there and there's not a current and there's not a red magnetic field, even if none of those things are there, if just empty space, my EMF will still be there. And if my EMF is still there, I still have that voltage, I'm still going to have an electric field, because this relation right here that relates voltage to electric field, it doesn't matter what's in that delta X. It doesn't matter if there's metal for current to be generated or not. If I have a voltage, I have this electric field spread out over that length. Sound okay? Okay. Looking at this picture, my yellow line is where my electric field is. What length is it extended over? If I asked you for the length of the yellow line, what would you tell me? The circumference of that circle, right? And in this case, it wouldn't be R2 that we'd be looking at. It's going to be R1. So this delta X is going to be circumference 2 pi r. 2 pi r. That's going to be R1, because what we really care about is the area that the magnetic field is over. Yeah. No? No. I got those flipped. I'm sorry. This is R2. That's R1. Much better. And the reason is we're looking at the electric field right there. So we care about R2 for this one. For this guy, this should be R1, because that's where the magnetic field is. Outside of that, there's no magnetic field. And so we want to include that in our flux calculation. Sorry, got those flipped. My bad. Okay. Okay. All of this put together, now we can talk about what this question is asking us, which is, what's the electric field at R2? And so we are going to write down this rule right here, where we have our electric field multiplied by the distance it's extended over equals negative ddt times the magnetic flux. And you have told me correctly that the delta X is 2 pi R2. So I have E 2 pi R2, and that the derivative of that magnetic field is this thing over here, negative pi R1 squared dTB. And so from this, we can definitely solve for the electric field. Where the electric field, my pi's cancel out very nicely. I have R1 squared at the top. I have 2 R2 at the bottom. And I have a dB dt right there. So that's what my electric field looks like at point R2. Now, a few things here. For this particular problem, they want you to call dB dt R sub 8. And they also just want the magnitude of the electric field. So if I just want the magnitude of this electric field, I would just drop the minus sign. And if dB dt is really R rate, I can just plug that in like that. Okay, does that make sense? So that's actually what they want. Okay. Okay. For the problem, are we happy? Number 15 is good. And then for just like the idea that electric and magnetic fields are related. Okay, excellent, excellent. Moving on. Let us talk about, I want to talk about emotional EMF. Okay, that's where I want to be. So, emotional EMF. I have two things I really want to look at. I don't want to, there we go, emotional EMF. Which is it's actually kind of an interesting concept as a whole. Mainly because I'm not 100% sure why we care deeply about it. It's a good way to talk about mechanical versus electrical power. And so that's kind of what we're going to be looking at. So I have some region of space where I have a magnetic field directed into the board. And I'm going to put a conducting metal bar. So this is metal. Electrically neutral at first. Well, it will be electrically neutral. And so it's going to be L long. And then I am going to physically grab this bar and I'm going to move it with a certain speed that way. And so that's where the mechanical part is. So I am mechanically moving it. Let's talk about what will happen electrically though. So this bar is neutral, but it is full of positive and negative charges, just like anything. So if I had a positive charge right there, and I started moving it that way in a magnetic field in that direction, a magnetic force would be exerted on it in the QV cross B direction. So which way is the magnetic force on this positively charged particle going to be in? Up. V cross B, up. Excellent. So there's going to be a force that way. And if I had a negative charge, I'd still do the V cross B, but then I'd multiply that by a negative sign, and I'd get down. So I have this situation where positive charges are going to be forced to the top of this rod, and negative charges are going to be forced to the bottom of this rod. So that as it moves, the top of it will become positively charged, the bottom of it will become negatively charged. There will be an electric field induced across it from the positive to the negative side. And of course, that will make a voltage as well, where the voltage, delta V, will be the electric field multiplied by the length that it's extended over, which is the length of that bar. Okay, so things kind of to think about here. I'm about to come up with we're about to write down an equation, but the big thing is I made this voltage, which can do work. Like we can hook this up to a circuit. I can like light a light bulb with this voltage, but I made the voltage by mechanically moving it. So I put energy into moving something, and I get energy out in the form of electrical current. Sound okay? This is one type of generator, where if you move a conductor around a magnetic field, you can generate a current. Okay. And in particular, I would like to talk about the relationship between the speed at which I can move this thing and the voltage that I am going to produce. Because I'm sure you're going to kind of get that the faster I move it, the bigger the force exerted on it. But once positive charges start collecting together, they're not going to want to move together more. So there's a force trying to oppose that. So if you're moving this at a specific speed, say I'm moving this at 2 meters per second, I will reach this steady state when as much charge as possible has collected on either end for that particular speed. Because for that particular speed, there'll be a force, a magnetic force in one direction. But then there'll be an electric force in the opposite direction. Where when you have a bunch of positive charges together, they want to push each other away. Do you guys remember the equation for electric force? It's a while ago. Okay, no, it was a while ago. Electric force is the charge multiplied by the electric field that it is in. And so in this case, we mean that electric field right there. Okay, so this will be QV cross B, and this will just be QE. When I say it reaches a steady state, what does that mean? Okay. If it reaches a steady state, would you expect more charge to collect on either side? No, okay, it means I reached a balance. Nothing is changing now. So in this case, when we're looking at forces, what we really mean is that the acceleration is equal to 0. So the acceleration of those charges is equal to 0. And so the net force, which would be the magnetic force in one direction and the electric force in the other, would add up to 0. So steady state in this case means that my forces are balanced. Excellent. Okay. And if my forces are balanced, I can start plugging in for their equation. So I have QE on one side. On the other side, I'm going to have QV cross B. But really quick, doing that cross product, I would get QV B sine theta. And what is the angle between my velocity and my magnetic field? 90. Sine of 90? 1. So I can ignore the sine of theta. Excellent. And ULT cross producted, right hand ruled your way into the correct direction. Okay. What's happening to the Q's here? They cancel out. And so it doesn't matter if I have a big charge carrier or a small one. And it also doesn't matter if my charge is positive or negative. Because if it was negative, my forces would just flip in opposite directions, but they'd still be in opposite directions. So the charge doesn't matter. I'm left with the velocity times the magnetic field equals the electric field. But I didn't want to talk about the electric field quite yet. I wanted to talk about the voltage. And so I have to go back and I have to say, well, the voltage is the electric field multiplied by the length the electric field extends over, so the length of that bar. Or in other words, the electric field equals delta V over L. So I have the velocity. I'm trying to like keep my V's separate. Sorry if it's a little awkward. Over L, where L was the length of that bar. And so I'm gonna, usually we see this written as the voltage equals the magnetic field times the velocity times the length of the bar. So if you wanted to generate an EMF, you now can do it depending on, you know, what sort of magnetic field you have, what sort of bar you have to work with, and how quickly you can move it. Reasonable? I hope so. And if that is reasonable, let's talk about how you would use it. Because how you would use it, okay, is you make yourself a railgun. Where you have, so you have this set of rails hooked together on one end with some resistor. You say the length of this side is L, and you give yourself a magnetic field. So you put this whole thing in a magnetic field. Okay. And then you give yourself a bar. And so the idea of this bar is it sits across the rails, so it makes an electrical connection with those rails. Sound okay? Okay. Now, we know that if you move this guy with some velocity, it will make an EMF across that bar. So we know that it is going to make a voltage equal to the, how did I write it down before? I don't know. The velocity times the magnetic field times the width of those two rails. Okay. Could we figure out how much current goes through that resistor at this point? Maybe. We could, right? Because this thing is making a loop where this entire bar is acting like a battery. It's acting like it's just a battery like that. And so we could just do like V equals IR. So voltage equals current times resistance, where the current would be this voltage, VL velocity, over the resistance. Okay, so far so good. So if we mechanically pull that bar out, it will generate a current. Now I said this was a railgun, and a railgun is really the opposite thing. If you put a current across this, it will move the bar. Sound okay? But I'm hoping what you're really excited about here is you're seeing a way to generate current, because that's actually like a really fundamentally important thing that we need to do as a society to keep our lights on. And so here's a way to mechanically generate a current, is just moving a bar across some rails. And you might say, how much energy will that generate? And in particular, you might want to say how much power instead of energy, because that's actually generally more useful. So really quick, let's talk about the power generated in this circuit. So power, so we have power is current times voltage, current squared times resistance, or voltage squared over the resistance. So those are like our three, power equations. And so if I want to talk about the power generated in this circuit, the power generated, I would say, well, I have a current, I have a resistor, let's plug them into the equation. Okay, I have a current, velocity over R. So there's my current. I have a resistance R, squaring it all up, I get this. Okay, by itself, maybe not super excited. But the next thing I want to look at is I want to talk about how much power or energy that you have to put into. So power generated, power taken up. So power out versus power in. Now, just with your knowledge of physics, if this generates VL squared, let's say X amount of power, how much power do you expect to have to put into the circuit?
I don't know the exact number.
Well, let me say this a different way. If I tell you that this circuit generates 10 joules of energy, so I have 10 joules of electrical energy coming out of that circuit, how many joules of energy do I have to put in? 10, because energy is not created or destroyed, right? And even more than that in this, the rate at which energy goes out of this circuit is going to be the same as the rate of that energy going into the circuit. And so let's check that. So this is going to be a mechanical power. And the way you calculate mechanical power is you multiply force dot velocity. I don't know if that was mentioned in your mechanics course. It was mentioned like in 2 seconds in passing. But that's how you calculate a mechanical power. Where if you think about this force applied, so that's the person who's actually moving it. That's the force applied. And to actually move this thing, you have to push it with at least as much force as it's being pushed back. So let me ask you a question. Let's go back to here. Go back to here. Am I doing this? Oh, no, let's go back. There we go. I'm doing here. I have a current going this way through this circuit, right? It is a current in a magnetic field. And so I have I L cross B. And so there will be a magnetic force on that in the L cross B direction, where L is in the same direction as I. So if I have a force in the L cross B direction, what direction is that force in? If my current is towards the top of the page and my magnetic field is into the page. Right, so yeah, current, magnetic field, forces that way. Or current into the field, yeah, forces that way. Excellent, excellent. So my magnetic force is actually that way. And then there's like a full circle here that we're doing, where when you're pulling that rod across that page, what you're doing is increasing the magnetic flux through the red loop, which of course, this current is being generated to try to cancel out that increase. And so there's a force trying to push it back to where it started. Does that make sense? So all of this is this idea that when you change something, when you change a magnetic flux, the universe wants to change it back. So you pull that bar out, there's a magnetic force trying to push it back in place. And when you're pulling it out, if you want to keep pulling it out, you have to push at least as hard as this guy is pulling back on. So the force applied has to be at least I times L times B. So current times L times B. Okay, and we know what current is. So current is BL velocity over R. And we're multiplying that by B, by L, and by B, and by the velocity. And I'm hoping you see that that'll give us a B squared, an L squared, a velocity squared divided by the resistance, which is exactly what you guys predicted, that the power coming out of the circuit needs to be as much as the power that you're putting into the circuit. Is that all right? Okay, okay. And you might say to yourself at this point, well, then that's a pretty useless machine because you have to put just as much energy into it as energy you're going to get out of it. But can you guys really quickly tell me why this might not be useless? Like how would you use this to generate electricity? Dude, you guys are in California. You should know this answer.
That's the funny part. I know.
This is the land of windmills, guys. Yeah, so you look at the world around you and you find yourself a convenient thing where you're like, I know there's going to be a force here. Let me try to capture it. Let me like put a windmill out in a windy area because I know that force will cause something to move. And that way I can take that mechanical energy, transform it into something more useful to me, which is electrical energy. That okay, good, excellent. I'm glad that makes sense. Is everyone kind of okay here? Excellent. Moving along. I think I can wait on this. I cannot wait on this. Let's end this up, and I might really finish on Thursday. But let's end this up talking about generators and motors. That's the last thing I really want to talk about for this chapter. Where you guys saw a motor in lab last week. Do you remember that? Maybe not even last week, the week before last. Sort of? Can you describe it? Yeah. So there was three components to that, right? Like you said, there's a battery. Yeah, okay, and then like the thing that holds up the wire is really just like to make a complete loop. And there was one other part to it. You might not have seen because it was cleverly in the casing. The magnet. There was a magnet right here. So what you had was a current flowing through this loop with a magnetic field. So as this thing spun, it either wanted to align with the magnetic field, or remember half the wire was insulated, or the insulation would kick in and the current would stop all of a sudden. So let's look through this. I'm gonna look at a generator first, and then we're gonna say motor is just the opposite. But this is what you need to make either. This is what you need for a generator motor setup. You need a loop of wire, you need a magnetic field, and you need a way to either provide current or take current in, one or the other. So let's look at a generator first. Which that last thing we just did, that whole motional EMF thing, that was a generator as well. Like that, you were generating currents. However, that is usually not the most convenient way to generate current, because if you think about if you have to move something along in a straight line, that's not very inducive for space. And even like I immediately started talking about windmills. Windmills rotate. And so rotations are usually much more convenient as generators than straight line sort of things. Okay, let's see what we got. I have my magnetic field. I have a loop of wire like this that has an area vector that's initially, that I'm going to put in some initial direction, such that there is an angle theta between my area vector and my my magnetic field. It also has wires coming off each end, just like we had on the other one, where you're gonna hook that up to your light bulb or whatever you want to power. Okay. Then what's going to happen is you are going to spin this. So this is a generator. So this is you're going to apply the force to spin it via windmill or hydroelectric dam or something, where you can talk about this angular velocity omega as the change of that angle with respect to time. Does that make sense? Okay. Okay, cool. Now, I'm hoping that you guys see this and say, we have to have some sort of Faraday's law here. So let's look at the flux going through this loop of wire. So it'll be the magnetic field, B, dot the area vector, A. And so that'll be the magnitude of the magnetic field, the magnitude of the area, which we could say it's a loop, it's pi r squared, but let me just leave it vague. And then the cosine of the angle between them. Now, throughout this chapter, we've been ignoring those thetas. Can we ignore this theta? Is this a theta that will just always be 0 or always be 1 or something? No, right? Because yeah, that angle is going to change as you go around, where sometimes this loop will be oriented like this, so the flux is 0. And sometimes this loop will be oriented like this, where the flux is at its maximum. So as long as this thing is rotating, this flux is either going to be decreasing or increasing as it goes around. Make sense? And if we wanted to know how it changes with respect to time, what we're really asking is what sort of EMF, what sort of voltage is this thing generating? So I have this flux, which right now is VA cosine of theta. If I want to know what sort of voltage I'm going to generate here, I just need to take the time derivative. So this magnetic field, it's a constant. Okay, what about the area of that loop? Constant. What about cosine of theta? It's changing. Okay, so when we're doing this derivative, we take the b and the a outside, and then we take the derivative of cosine of theta. And what is the derivative of cosine of theta? Say again? No. I think you said it right. Omega sine? Oh, negative sine. Excellent. Okay. Negative sine. But then we also have to take the derivative of the inside, right? So we take the derivative of the cosine, and then we take the derivative of theta. So I have a d theta dt. And a lot of times you don't have to do that. If your theta was constant, you wouldn't have to do that. but our theta is not constant. So I have, those minus signs go away, I have B times A times omega, the angular velocity, times the sine of theta as my EMF. Now let me ask you a few questions. One, if I spin this faster, do I get more voltage or less voltage? If I spin this faster, which of these variables tells me how fast I'm spinning? How quickly I'm spinning? Which of these variables says that?
Omega.
Yeah, the omega, because that's angular velocity, right? So that's how quickly this is spinning. So if I want a higher voltage, I need to spin that faster, which might be a problem because I can't make the wind blow any faster. So the other game you can play is you can put multiple loops of wires, and you would, because for every extra loop of wire you add, this goes up by a factor of n. So if I have 2 loops of wire, I've doubled it. If I have 3 loops of wire, I've tripled it. So I would always just add in that extra n. And I need to wrap this up, but let me add to the end of this. Just as this omega is d theta dt, this theta, we can call it omega times time, right? So a lot of times you'll write this voltage with respect to time. So sine omega t, like this. And this is going to become important in 2 weeks when we start doing AC circuits, where we're not always going to have like 10 volts across our circuit. We'll have a sine wave going from positive 10 volts to negative 10 volts. And this is how you make one of those. Okay, I'm out of time. Any questions? Okay, I will see you on Thursday. We don't have lab on Thursday. No lab. Oh, there was never a lab. There's Veterans Day this week, and so we just don't have lab this week. No lab. We meet again next week.
We were having a lab this week, but
Coding. We're gonna do a coding lab next week. Yeah, gonna do a little code.
I'm fine with that.
Calculate a few integrals.
Thank you.
Graph some stuff. It'll be great. Oh, we're going to.
With Python or R.
Oh, more Python-y than R. We're actually going to use Mathematica, but frankly, it looks pretty Python-y.
Anything to put in my resume.
This is probably actually the most useful